Today I am going to discuss about the intersection of algebra and physics. So my presentation topic is supersymmetry and Lie superalgebra. Before I begin, I just want to tell you that my focus of this study is particularly algebraic structure of Lie superalgebra, particularly on the concept of isoclinism that I have done. Now I want to connect supersymmetry with my portion of uh, research, that is isoclinism. So this supersymmetry is completely new for me. Universe is made up of teeny particles. Two kind of particles are there, fermions and bosons. Actually, these are the completely two different particles in behavior. But supersymmetry suggests that these are the two sides of the same coin. And fermions are the particles that made up matter, and bosons are the particle those carry charges. For example of fermions that are electrons, protons, and example of bosons, examples of bosons are the photons that carry charges, sorry, light, that carry light. Photons carry charges, that carry forces, that we can say. Okay. So now we are just want to discuss about the mathematics behind this supersymmetry. Previously, about the symmetry concept, the mathematical part was defined by this commutator relation, that xy is equals to xy minus yx. Now we got another operator, that is a fermionic operator, and these particles are not satisfying this bracketing condition. This satisfy this another bracketing condition known as anti-commutator. So algebra that is satisfying this both the condition commutator as well as anti-commutator, that gives us the concept of Lie superalgebra. About a Z2 graded vector space, a vector space can be decomposed as two of its subspaces V0 and V1. This V0 is known as the even part and V1 is known as the odd part. Any element belongs to this superspace that carry some grading, parity or degree. If element belongs to V0 part, that is with degree 0, and if element belongs to V1, that is with degree 1. So a superalgebra is a superspace that is satisfying this gradation property. If we are taking a mixture of two different or same kind of element, what is the result of this? Next, about Lie superalgebra, that's a superalgebra, that is Z2 graded vector space that cubed with this bilinear map satisfying these three conditions. Number one is Z2 gradation property. It shows the what is the gradation of the complete bracket. Second is graded skew symmetry property. This property shows that if two elements, if we are interchanging two elements of this commutator bracket, how they will act. And third property, graded Jacobi identity, shows that although we are taking a mixture of elements of different gradation, that time also this consistency of algebra will be satisfied. This is how we have how this commutator bracket is defined. This is known as supercommutator, that with some parity. So if we are considering two even elements, so we will get even odd mixture also we will get this normal commutator bracket. When we will take two odd elements, at that time we will get anti-commutator. These are some basic terminologies of Lie superalgebra. In this Lie superalgebra, L0 part is just ordinary Lie algebra. And abelian Lie superalgebra is the super in which all the elements will commute with one another. Center of Lie superalgebra, that will contain the set of elements which commute with every other element of that Lie superalgebra. Derived subsuperalgebra, that is the set of linear combination of that Lie superalgebra. Homomorphism is an even linear map that satisfying this bracketing condition. Steam Lie superalgebra, when center of Lie superalgebra contain in its derived subsuperalgebra. Basically about the super dimension of Lie superalgebra that we defined by P by Q form, where P is the dimension of the even part and Q is the dimension of the odd part. This is isoclinism. First we are considering two Lie superalgebras and we are having two homomorphism mu and nu. This is from the quotient map, this is from the derived map, such that this diagram should be commutative. Nu sigma is equals to rho mu square property should satisfy. When they are homomorphism, then this is said to be homoclinism. If these two maps are isomorphism, then we will say this structure isoclinism. So from the definition of isoclinism, it is clear that whenever we are considering two isomorphic Lie superalgebra, definitely this isoclinism will be satisfied. Now, the question is whether the reverse will satisfy. When does this isoclinism imply isomorphism property will be satisfied? In basically, isoclinism is weaker condition than isomorphism. So, in our research, this is the main result that we have done, that first of all, we are considering an isoclinism family. In this isoclinism family, any Lie superalgebra can be written in this form, that can be written as the direct sum of steam Lie superalgebra and an abelian Lie superalgebra. Steam Lie superalgebra where center contains derived subsuperalgebra means basically this is the non-abelian core of this superalgebra. And now I am trying to connect this thing with supersymmetry. In supersymmetry, whenever we are writing L0 direct sum L1, L0 is the even part and this even part defines the bosonic part of the supersymmetry and L1 is about the fermion part. So this T is the steam, that is the non-abelian core of this superalgebra where all the symmetries actually exist. This will show us the interactions of the transformations. This will contain the non-abelian part of this superalgebra. And in A is the abelian superalgebra. And next result shows us that if we are taking two finite same dimensional with same degree Lie superalgebras, then this isoclinic imply isomorphism condition will be satisfied. We can see this by one example that we have considered two different dimensional Lie superalgebras, L and K. This is with 2 by 1 dimension, that is defined by this commutator relations. We can see its derived part L square will contain L1, L2 and its center is equals to 0. And next Lie superalgebra, that is K, 3 by 1 dimensional with these two commutator brackets, and by comparing these two we can get that this L square isomorphic to its commutator K square and L by ZL, that is isomorphic to K by ZK. So we can say that this structure is isoclinic. But as dimensions are different in both the superalgebra, so these are not isomorphic. Basically, if any of the property in between dimension and degree is not satisfied by the superalgebra, then this if and only if condition will not be satisfied. So actually I want to extend this concept of isoclinism for higher dimensional case. For this higher dimensional case, for n I have already studied. This isoclinism concept actually used to classify the algebraic objects, that is based on the commutator bracket, not on the isomorphism concept. By the commutator relation only it can classify the algebras. So whether we can classify these things for higher dimensional case, and another thing that how we can connect these things with the supersymmetry. So as I got the opportunity to come here, so I had some question, that's why I came with these questions. If anyone will be interested, he or she can give me some suggestions regarding this or
questions.
yes, ma'am.
My question is some particles with mixed statistics.
Yes.
Like anyons.
Oh.
How would it map it to? Your super algebraic this thing, how
If that is mixed at that time also, this property will be satisfied. That mixed will also belong to either even or odd particularly, because we are
even
considering
and
here
odd,
Z2.
what did you precisely mean by even and odd? Can you clarify?
Even or not.
Even and odds, you showed some commutators.
Okay,
right?
okay. This one.
Yeah. Who did map it to?
If both the elements are even at that time we are talking about, its degree will be 0, 0. If you are considering odd element, degree will be 1. So this bosons and fermions are mainly
But
differentiating by the
I am
spin.
talking about mixed statistics, anyons.
No idea regarding that now.
Something.
Yeah, so I want to understand so how the dimensional reduction something can modify the structure of this Lie superalgebra in your work.
Dimension.
Reduction, right? Is it can modify the structure of your superalgebra?
Sorry, not able to get. As we are presenting the dimension in P by Q form, P
Okay.
represent the even part and Q represent the odd part.
Yeah. So there must be two type of different field. One is
Yes, yes.
commuting and anti-commuting.
Yes.
Okay. Yeah. So is it something can modify the because structure of your Lie algebra? That's something.
As this Lie superalgebra concept we got from supersymmetry. So
Yeah.
definitely L0 direct sum L1 always we have to write. And basically graded algebra is also there. On there we can take more gradation. That integer also we can take.
Okay.
So these are the works that I have done in this isoclinism. Thank you.